In example 4, you saw an instance of using a graph to evaluate compositions of functions. Here you're using formulas, which is what you're going to see a lot of as well. And I mentioned it in the previous video, but this video is going to kind of walk you through that process a bit more. So here you're doing g of h of 3, and you can see that g of t is going to be 9 minus 2t, h of t is 4.5 minus 0.5t. So g of h of 3 would be written this way as well, which means I'm going to start with h of 3, which means you're going to go to the function h of t, replace the t with a 3. So you're going to be doing g of 4.5 minus 0.5 times 3. That's going to give you a 3 in there. 4.5 minus, which is going to be 1.5, is going to give you a 3. That's going to now be g of 3. So not done yet. I have to go one more step. G of 3 means go to this function, replace t with 3 now. And so I'm going to have 9 minus 2 times 3, which does give you 3. So notice here that when 3 was put into the composition of these functions, you got back 3. That's going to make doing h of g of 3 in this instance a little easier, because when you do h of g of 3, well, we saw up here g of 3 eventually became 9 minus 2 times 3, which gave us the value of 3. So I know that g of 3 is going to become 3 in here. Well, when we did h of 3 in here, that's how we end up getting the 3 inside this parenthesis up here. So that equals 3. So it seems to work the same way. When 3 was plugged in to the composition of h and g in this direction, you get back the original value. It's behaving like these two are inverses of each other. And if they're inverses of each other, that means that one essentially undoes everything that the other one does. So let's see if they're inverse functions of each other. So if I do g of h of t now, instead of doing it for one single value, I'm going to do it for all values of t. That means that you're going to have g of h of t, which is the same thing as g of 4.5 minus 0.5 times t. Now, because you don't have a number to put in for t here, you can't simplify this anymore. So this is a simplify you're going to get for what's inside the parentheses. As far as doing the function g now, I'm going to go back to g of t and now replace t with what's in here. So that's going to give me 9 minus 2 times the quantity, 4.5 minus 0.5t. When that's worked out, you get 9 minus 9 plus t, which becomes, of course, t. When you do h of g of t, of course, is 9 minus 2t, so that's what goes inside the parentheses here. And when you work this out, you're going to put 9 minus 2t in the place of t up here. So you're going to end up with 4.5 minus 0.5 times 9 minus 2t, which is going to give you 4.5 minus 4.5 plus t, which of course becomes t. Anytime that you get the composition in both directions, taking the value t and returning the value t, that means that because both of these occurred, these two functions, g of t and h of t, are inverses of each other. So when you're looking at situations where it says, okay, you're given these two functions, f of x being 2x minus 3 and g of x equaling 1/2 x plus 3, it's asking you to do f of g of x, g of f of x, and to answer the question, are these inverses of each other? And a lot of people, they'll look at these two and they'll say, well, it looks like they're inverses. This one is multiplying by 2. This one's multiplying by 1/2, which is dividing by 2. This one's subtracting 3. This one's adding 3. So it seems like everything this one's doing the opposite. But remember, sometimes when you're dealing with these things and dealing with things that go inside and outside of parentheses, the order in which they occur does matter. So when you're looking at f of g of x, which is the same thing as doing f of g of x, written like this, well, g of x is just 1/2 x plus 3. Can't simplify that what's inside here anymore. So this is going to be substituted in for x in the f of x function. So that's going to become 2 times 1/2 x plus 3 minus 3. So the x was replaced with 1/2 x plus 3. Distribute the 2, you get x plus 6 minus 3, which is x plus 3. This is x plus 3. For f of x and g of x to have been inverses, this would have had to equal x and just x, no plus 3 at the end. So right now, we could answer the question C. No, they're not inverses, because the composition did not take x and return x only. It returned x plus 3 when I did f of g of x. When I do g of f of x, again, I'm going to replace f of x with what it is. It's 2x minus 3. That can't be simplified inside this quantity anymore. So this means I'm going to do g of 2x minus 3, which means I'm going to go to the function g of x, replace this x here with 2x minus 3. So I'm going to have 1/2 times the quantity, 2x minus 3 plus 3. Distribute the 1/2, you get x minus 3/2 plus 3, which gives you x plus 3/2, which is the same thing as x plus 1.5. So you can either put x plus 1.5 or x plus 3/2 up here. But that's still not equal to x in x alone. So that's yet another reason why you could say these are not inverses, because for them to be inverses, both of these would have had to have equaled x. Now, one of the things that they mention also is that you can have functions that when you take the inverse of them, you don't end up with a function. If it does that, if you end up with a function that if you find its inverse is also a function, it's called one-to-one. Now, there's algebraic ways of handling it, but one of the ways you can often tell if a function is one-to-one, the easiest way is to look at a graph of it. Here you're given a graph of f of x. It looks like it's some sort of absolute value function. We've played with those before. Is it one-to-one? Well, it's definitely a function. We're told it's a function. It does pass the vertical line test. The vertical line test tells me it's a function. However, when I do its inverse, I'd be switching all the x's and y's. And what that would do is turn this thing more or less sideways. And if it was turned sideways, it would not pass the vertical line test. The inverse wouldn't. Well, one way we could do that without doing all that work of switching all the x's and y's, redrawing it, and then doing the vertical line test again is to apply what's known as the horizontal line test. If I have a function, it has to be a function, and I pass a line, horizontal line through that function, if it only intersects once, then the inverse of that function would also be a function. Here, this fails the horizontal line test. That horizontal line is intersecting in two places. Because it fails the horizontal line test, the inverse of f of x is not a function. And because the inverse of f of x is not a function, this is not one-to-one. You're going to look at other ways of how to determine if things are one-to-one or not as you do the homework and look through other examples of in the textbook and other things you're working through. But generally, that's how you determine if it's one-to-one. The inverse of the function has to also be a function. That is the end of this problem in this example, and that is the end of this video. If you have any additional questions, please make sure to bring them up during class.